Next, we will consider uh, answer of question number 26.3. That is a sample drawn from a population following the distribution fx theta is equal to e raised to minus m raised to x by x factorial x 0, 1, 2, 3, etc. Please treat this m as theta. This is the equation of Poisson distribution, and the equation has to be considered as e raised to minus theta, theta raised to x by x factorial. Here the question is to show that sample mean is a sufficient estimator of population mean. We shall come to the answer of this question. Okay, so this is the density function fx theta e raised to minus theta theta raised to x by x factorial x 0, 1, 2, 3, etc., which is the equation of Poisson distribution. Now to show sample mean is a sufficient estimator of population mean, first of all we'll consider the sample x1, x2, etc. xn means a set of variables representing the sample that was drawn from the respective population, that is with the density fx theta e raised to minus theta theta raised to x by x factorial. Now its likelihood function is given by pi I is equal to 1 to n f of xi theta. That is because here the likelihood function is by definition is a joint probability distribution of the sample. It's a multivariate probability distribution, and here the variables considered in this multivariate probability distribution are independent random variables because the sample was drawn in random basis. Therefore, we can consider this multivariate probability distribution as product of individual distributions, that is distribution of x1, distribution of x2, etc., distribution of xn, or product of this distribution of x1, then distribution of x2, etc., distribution of xn. That's how we have the equation pi I is equal to 1 to n f of xi theta. And each of these variables will have the same distribution of the population, that is the Poisson, because all are coming from same population. Therefore, they will certainly inherit the distribution of the population. That's why we have the next equation e raised to minus theta, theta raised to x1 by x1 factorial, e raised to minus theta, theta raised to x2 by x2 factorial, etc. e raised to minus theta, theta raised to xn by xn factorial. Now, when we collect the similar terms, we get e raised to minus n theta, that is e raised to minus theta here appearing n times. So it is e raised to minus n theta, theta raised to sigma xi by pi I is equal to 1 to n xi factorial. So we rewrite the same equation in terms of x bar. So it is e raised to minus n theta, theta raised to n x bar by pi I is equal to 1 to n xi factorial. Next, to show this x bar is a sufficient estimator of theta, we have to factorize this likelihood function into L1 and L2. For L1, the first factor is a function of the proposed estimator and also the the parameter being estimated. That is L1 is x bar comma theta, and L2 is a function of x1, x2, etc. etc. That may be anything other than the parameter theta. That must be independent of the parameter theta. So if you write L1 as the numerator side, e raised to minus n theta, theta raised to n x bar, and L2 as the downside, that is 1 by pi I is equal to 1 to n xi factorial, the terms appearing the downside, that is denominator. Then we are able to factorize L as two factors, L1 and L2, or the condition required according to Fisher-Neyman factorization theorem. So we have x bar sample mean as a sufficient estimator of uh, the parameter theta, that is population mean. Here this theta is the mean of the Poisson distribution, so population mean theta. Next is a question of related to normal distribution, that is sample mean x bar is a sufficient estimator of population mean when sigma square is known, while sample variance square is not a sufficient estimator of sigma square when mu is known, where mu and sigma square are the mean and variance of a normally distributed population. So first of all, we write the equation of the distribution, that is normal distribution. Distribution of the population is given as normal. So this is the equation. Now we have the sample drawn from the population following that normal distribution. So that is the equation of the likelihood function. So we have the product of n density functions, that is 1 by sigma root 2 pi e raised to minus 1 by 2 x1 minus mu by sigma square into 1 by sigma root 2 pi e raised to minus 1 by 2 x2 minus mu by sigma square, etc. 1 by sigma root 2 pi e raised to minus 1 by 2 xn minus mu by sigma square. That is by considering the terms, similar terms together. So 1 by sigma root 2 pi whole raised to n e raised to minus 1 by 2 sigma square. Sigma is equal to 1 to n xi minus mu the whole square. That's by considering that 1 by 2 x1 minus mu by sigma square plus 1 by 2 x2 minus mu by sigma square, etc. Now, in order to show sample mean is a sufficient estimator and S square is not a sufficient estimator, first of all we should bring those estimators in the equation of N. At present they are not available, they are not present in the equation. So in order to have these x bar and S square in likelihood function, we do some modifications here, and that is done in the terms given in the power of this exponential, that is sigma is equal to 1 to an xi minus mu whole square. So we add and subtract an x bar here, so nothing happens to this, the equation will be balanced. Now expanding this, sigma is equal to 1 to an xi minus x bar whole square, this is considered as A and this is considered as B. So sigma is equal to 1 to n x bar minus mu whole square plus 2 sigma is equal to 1 to n xi minus x bar into x bar minus mu. We can see that this is the equation of n square because this is the equation of s square. So definitely this is n square, and as far as the summation is with respect to I, this can be considered as a constant. That's why n into x bar minus mu whole square. And when you come to the last term, it is 2 sigma is equal to 1 to n xi minus x bar into x bar minus mu. But this x bar minus mu can be kept aside, that is outside the summation of summation. So it is actually sigma is equal to 1 to n xi minus x bar, and that is the sum of deviations taken from mean, which is 0. So in short, the last term will disappear. That is n square plus n into x bar minus mu whole square. So when we write the likelihood function, we get it is 1 by sigma root 2 pi whole raised to n e raised to minus 1 by 2 sigma square n square by n square plus n into x bar minus mu whole square. We rewrite the same equation in three terms, product of three terms. One is 1 by sigma root 2 pi whole raised to n. Second is by removing this bracket, so e raised to minus n square by 2 sigma square, and the third is e raised to minus n into x bar minus mu whole square by 2 sigma square. Now we consider factorizing of this likelihood function. We can treat that L1 x bar minus mu and L2 x1 x2 etc. xn, where L1 x bar minus mu is the terms, the term containing x bar and mu. So e raised to minus n into x bar minus mu whole square by 2 sigma square. And L2 is some function not containing the estimator, no, the parameter mu, not the estimator. The present parameter is mu. And you can see that in the first function L1 we have x bar and mu. So that's quite admissible because x bar and that L1 is supposed to be a function of x bar and mu. Other than this x bar and mu, we have the sigma square, a second parameter. Actually, this is not to be admitted in L1 because L1 must be a function of only the estimator proposed and the parameter being estimated, that is x bar and mu. So actually this is an encroachment. Sigma square is an infiltrate. We have to say that. We will say in that is 2 sigma square, not 2 sigma square. But we can treat it as a constant like 2, since in the question we are given sigma square known. So when a parameter is given to be known, it cannot be considered as a parameter. It can be treated as some constant of that function. So sigma square is just like 2 or n, like that. So therefore, this is only a function of x bar and mu. At the same time, in the other side, you can see that L2 is a function other than without this, the parameter being estimated, that is it's only a function of s square, that is another function in x1, x2, etc. xn. That's how we get uh, x bar. Sample mean is a sufficient estimator of population mean when the second parameter sigma square is known. Now we consider the other side, that is what happens to sample variance when the other parameter mu is given. That is, can we treat sample mean as a sufficient estimator of sample variance as a sufficient estimator of population variance. So again we think of factorizing this likelihood function with one factor as a function of s square and sigma square, and the other factor not not with sigma square. So when we look upon this equation, we can see that in all the three factors we have sigma or sigma square. So in short, we have to take all these together in L1, and L2 is 1. That's one way. But we see that when we take all these L1, all these terms as L1, we have sigma, okay, it is admissible, root 2 pi, no problem, because constant, n square by 2 sigma square, here also no problem. But you can see that even mu also will not make any trouble, because you can consider the second parameter mu as a constant since it is given. So who is the infiltrate here? That is x bar, because if you treat L1 as L, we have two functions of x1, x2, etc. xn. One is s square and second is x bar. We cannot remove s square. No, we cannot remove x bar from this L1, because these are all three molded items. One is 1 by sigma root 2 pi whole raised to n. Second is e raised to minus n square by 2 sigma square. Third is e raised to minus n into x bar minus mu square by 2 sigma square. So we have three terms, and of these three terms, never we can detach x bar from here and can take as a function of simply mu and sigma square, etc. Therefore, that will come together with all these terms. That means apart from the proposed estimator s square and sigma square, there is one encroachment of x bar into L1 which is inadmissible. Therefore, we cannot factorize L as two factors, L1 and L2, where L1 is a function of S square and sigma square alone, and L2 is independent of sigma square. That's why we get S square is an insufficient estimator of uh, sigma square. That's how we conclude here. L1 is, even though we take L1 as L itself, there will be the presence of x bar, which is another function of x1, x2, etc. xn, and s square cannot be considered as a sufficient estimator of sigma square when mu is known. And now, next is number 28. T equals 1 by n sigma is equal to 1 to n xi minus mu whole square will be a sufficient estimator of variance sigma square of a normally distributed population. Here we have very similar to that question number in the former question 27, that is L equals 1 by sigma root 2 pi whole raised to n and all, and we just make a modification here, e raised to minus n by 2 into 1 by n sigma is equal to 1 to n xi minus mu whole square, that is e raised to minus n by 2 into t, and t is the proposed estimator. So we see that L1 is L itself and L2 is 1. So nothing encroached here, because mu is given to be known. Since mu is known in this estimator, uh, no other parameter or no other statistic, no other estimator. And L2 is taken as 1, which is independent of sigma square. That's how we get T is a sufficient estimator of sigma square when mu is known. So when we consolidate the properties of the three estimators of sigma square, we have this table, that is the first estimator, the first candidate is Small square. Small square is not unbiased. It's a biased estimator, but it is consistent, but it is insufficient. When you come to the second estimator, that is capital S square. We found this capital S square along with a question of, in the list of questions, we have capital S square that is here. Number 15, it is an unbiased and consistent estimator of sigma square, that is capital S square. So we have the two tick mark for in the credit of S square. In the credit of S square, we have unbiasedness and consistency. The third candidate is T, which is having all the three properties: unbiasedness, consistency, and sufficiency. So as far as the things of now, we see that T, that is given as 1 by n sigma is equal to 1 to n xi minus mu whole square, is a unbiased, consistent, and sufficient estimator. That's theoretically, but when you come to the practical scene, you will see some unexpected performances. Okay, we can see that later along with the real estimation task. Now, number 30, show that sample mean x bar is a sufficient estimator of p, where p is the parameter of a proportion following binomial distribution. Uh, Here you have to also answer 29, 31, and 33 version. That is, questions very similar to the questions already discussed here. So we have the sample, now the likelihood function. Here in the equation of binomial distribution, we write n using k, because here this is to be taken as uh, k, not n, because n already considered with the sample size. So that's why we take binomial with the k and p. So this is the product. So this is the simplified equation. We consolidate similar terms. We write sigma xi as n x bar. So this is the equation. So this is L1 px bar del x1 x2 etc. So we can very finally factorize this L as L1 and L2. One is a function of the proposed estimator P and the parameter, sorry, proposed estimator x bar and the parameter P, which is being estimated. That's about the answer of question number 20, now 30. Now we have the last number 32, that is obtain a sufficient estimator of theta, where theta is the distribution of a population following density fx theta is equal to 1 plus theta x power theta, say less than or equal to x less than or equal to 1. Very similar lines we have the likelihood function, then the simplified equation of likelihood function, then factorizing this likelihood function, L1 as the full complete L and L2 simply 1. So T is a sufficient estimator of theta. That's the answer of the last question. Thank you.